I first learned about quantum sensing and navigation and GPS and GNSS, um, I got into a conversation via email with Gavin. And then later on, I was thinking, I bet a lot of people would be very interested in the same topic. So I invited Gavin to do this talk, and he graciously accepted that invitation. I'm very, very happy that he is here with us today. Gavin is also, by the way, the administrator of the Real-Time Network, RTN, for the state of Washington. And I'm going to stop talking and turn it over to Gavin for quantum sensing for geospatial applications. Thank you very much, Gavin, for doing this presentation for us.
Cool. Yeah, Keith, it's well, we had conversations about jamming, spoofing, and alternate PNT and all kinds of stuff. And I had been researching that for 2 years for a series for geospatial publications, but also for our own community here in Washington. So this gives me a chance, opportunity to test drive this abbreviated version, and it got me out of a division meeting. So, hey, happy to do this. So, yeah, the subject is the headliner was jamming and spoofing, but quantum sensing, because that gets a lot of airplay, the jamming and spoofing and the vulnerabilities, but we're going to try to put that into a little bit of perspective. There's a difference between what happens in conflict zones and what happens in our own states and towns. So is my screen being, yeah, my screen is being shared. So key thing about quantum sensing, when the word quantum gets used a lot in the media, it's typically they're talking about quantum computing. That is not the same as quantum sensing, although some of the same physics principles are applied in quantum sensing. Quantum computing is, this potential for it. It exists already, but it's, we deal in a digital world of classical bits, 0, 1, the Boolean. Well, with a qubit or a quantum bit, which is kind of excited particles, lots of interesting things happen. There's superposition. A particle can appear to be in two states at the same time. It's the Schrodinger's cat. Well, and then when you open the box, you find out if the cat is alive or not alive. But the qubit has so many more possibilities that can be analyzed or tried out. So the qubit, to give you an example, 500 qubits can perform like 2 to the 500 classical bits. So a classical computer could take millions of years to find the prime factors of a 2048-bit number. Qubits can do that in a couple of minutes. So there's all these interesting things about superposition, entanglement, and teleportation. Not what you're thinking. It's not like Jeff Goldblum turning into a fly or beaming up Scotty. But anyhow, over in the quantum sensing world, there's the two basic physics that happen there. Rydberg atoms, which actually got identified in 1880 after a Swedish physicist, Rydberg, where you take a laser and super cool an atom, and then a single electron will get an expanded orbit. And when it does, it becomes super sensitive. I mean, astronomically more sensitive than the individual particles in the coherent classic atom. The other one's cold atom interferometry. I'm still trying to get my head around that, where you've got excited particles that track two paths, and it compares them. And give you an example. In quantum sensing, these are used a lot. Okay, quantum sensing and quantum computing, a big difference here. Quantum computing is astounding, but it's large, expensive, extremely power hungry, not practical for any field geospatial devices, not for decades, maybe not even that. Keith asked to put this into perspective of like surveying and mapping and what all this stuff could mean to us. There can be benefits by extension to geospatial. For instance, imagine when cloud computing is run by quantum computers, if it ever gets there, so much more processing could be done so much faster. Encoding, classification, analysis, even GPS, GNSS, it can help with encryption that is being worked on right now. Over in quantum sensing, though, it's already practical. It's already the technologies have been proven. They got to work on miniaturization. There are foundation geoscience benefits, like by extension, if they improve the gravity model of the Earth, we get better elevations when we use GPS. You know, to get an orthometric elevation, you have to apply a Julia model to the ellipsoid observations. Alternate positioning, navigation, and timing, alternatives to GNSS or augmentations of, because, people are freaked out about vulnerabilities. Highly practical for enhancing timing and alt navigation, but positioning, though, we're going to find out that all of these alternatives, quantum or not, can't get the precision that we can get with GPS. But the good news is it's going to help in a lot of interesting ways. So in the geospatial world, surveying, mapping, GIS, we're going to see the benefits of quantum sensing a lot sooner than we will see it from quantum computing. So the basics of the devices are you have to have an ultra high vacuum chamber. And for these atoms to exist in and be excited, the lasers enter the chamber, they excite the atoms, and other lasers read what the behaviors of those particles are from those atoms. Beam splitters, clouds of atoms interact with these lasers, the expansion of the orbits of the particles, and then the processing of those signals. That's the fundamentals. So positioning, navigation, and timing, going back to this, that, GPS and GNSS is the primary mechanism globally for positioning, navigation, and timing. For timing, the world's clock runs through the GPS system. An array of 300 atomic clocks on the Earth comes up with a standard time that's conveyed to computing systems, international banking, navigation, everything through the GPS satellites with clock corrections. Now, the risk levels of the vulnerabilities like spoofing, jamming, solar activity, other things, the risk levels, they vary a lot depending on the application. Pretty much civilian and military applications, defense, that's where the vulnerabilities really hit hard. Civilian use of high precision, no. Navigation, that's that does happen. I'll give examples of that. Okay, the alternates to GNSS for positioning, navigation, and timing, it can meet these needs with varying degrees. Navigation, high precision is not required. You're talking about a ship-sized spot on a map. The alternate PNT, be that space-based or ground-based or quantum, can meet that. Timing, alternate precise timing is doable. The alternatives are typically satellite-based with encryption, different encryption approaches, or they require substantial infrastructure investments like running fiber backbones over a whole country to get the precise time spread about. Positioning, the alternatives are not high precision, or even if they're ground-based, are going to be subject to similar vulnerabilities. Quantum can be the foundation for some of the alternatives and improve some that already exist, even GPS. So because, Keith was asking specifically about jamming and spoofing and interference, I want to go over that a little bit. We got to assess the vulnerability risks to what we do in surveying and mapping and GIS. Okay, jamming, that's a deliberate disruption of the radio environment. Extremely rare beyond conflict zones. Spoofing, that's sending false signals. Again, really rare beyond conflict zones, and there's reasons why it's rare. And I'll give you an example of that. Interference, this is inadvertent disruption of the radio environment. It's still rare. A handful of incidents per year in North America. There's the famous incident in San Diego in 2007 where a ship in the port turned on some electronic warfare stuff, and that it disrupted a lot of things in San Diego for a very brief amount of time. The GPS, cell signals, all kinds of things. Then there was a deliberate case. A trucker in New Jersey bought a little cheap $100 GPS jammer to jam his GPS in his truck so his boss wouldn't know where he goes. Well, he went by the Newark airport. They picked it up in a hurry. They analyzed it really quick. They tracked it down, and he got a $38,000 fine for doing that. There's only been a handful of other trucker jammer incidents. So, assessing the vulnerability risks. There's an interesting website you might want to look at. It's called gpsjam.org. It analyzes the signals at ground stations, like reference stations in a network. We have spectrum analyzers on all of ours, I show in the middle there, and it plots it on a map. So if you look globally, you see the red spots there in Eastern Europe around conflict zone. In the United States, the lower left image, we're not seeing anything going on. There's a little bit that happens around some military installations and down by the border. The U.S. Coast Guard is the entity which takes in the reports of GPS issues and analyzes them and tracks them down. And the FCC, can go out and investigate something. You see the spots on a map over a year globally for navigation. And a lot of those, if you read the logs, a lot of them turn out to be somebody is not getting their GPS because they've got the settings wrong, or they've got it sitting inside in essentially a Faraday cage. Very few are actual incidents. The middle upper plot is there's a tool called Giant, a federal one that can analyze down to the granular level what would go on during jamming or interference. The military, they have special antennas like this Novatel called the Gadget that detects and then blocks jamming directionally. And on the right, upper right, we have, because we run a network, we have an interference tester. And when users go out there and they read articles about jamming and spoofing, they suspect things, and we take that out there and show them, no, there's not really anything going on. In our state, we only found 2 places where the signal will be disrupted. At the end of a big runway, international runway, where they have altimeter radar, only when the plane passes over, not only does your GPS not work, but your cell phone doesn't for a few seconds. Or by the Navy submarine base over on the peninsula. There's just one little spot. So there's highly hyped news reports about, oh, we're going to replace GPS. With what? Well, for navigation purposes, there's potentials using quantum technology for doing things like using the geomagnetic values mapped around the world, and the highly sensitive quantum sensor, which now they can build in a chip scale, can read that map and give you an orientation and a position. The challenge, though, is mapping it. To map to the detail where you get better than 100 meters of a position, you've got to use quantum sensors to improve the geomagnetic maps of the Earth. And those geomagnetic fluxes vary constantly, so it has to be updated all the time. So yeah, it works. It works, and it's going to be very helpful for navigation, but it doesn't apply to us in the precise positioning field. Another one is quantum navigation that you hear a lot about. It's a quantum gyroscope. What it's doing is it's sensing the displacement of those particles in a vacuum chamber as, say, a submarine is navigating. And this actually been deployed in the Royal Navy, and there's a lot of places building them. For instance, Imperial College over there on the left, I got to visit them, and it was fascinating. And there's a lot of great potential for this. Again, you can't get high precision. The best they can hope for is the size of a submarine, but it'll say where it is underwater anywhere in the world for a period of time before that solution drifts. Okay, other things that can improve other areas of mitigating and improving GPS and GNSS. So the highly encrypted signals is one thing that, especially for defense purposes, is going to help. But there's actually a neat application that we will be able to use in geospatial, in our daily work if we need it. If we don't have interference, we don't have to turn it on, or you don't have jamming or spoofing. Quantum antennas. This is pretty cool. This could make its way to GPS rovers when they miniaturize a bit more. The U.S. Army has developed, and others have developed quantum antennas over on the left. This one can read the entire radio spectrum. That means that it can differentiate and focus on exactly the signals that it needs. It's going to be harder to spoof, harder to jam, and it can also use opportunistic signals from other things, from cell towers, television transmitters, to help give you a gut check of that position. If somebody spoofs you 50 feet and using these other signals goes, hey, something's wrong. So spoofing detection, because it's super sensitive, also algorithmically in your GPS receivers with the highly sensitive detection, you can detect that the spoofing and ignore the false signals. And the other thing by extension is absolute gravimeters. So the geoid model of the world is really good. They've used satellite data, airplane data, cold matter detectors, fiber optic, but absolute gravimeters are nailing it down to, values where we're going to be sub-centimeter in a geoid difference model. The other thing they can do is they can profile with it. They can put one on top of another at a specific distance, make it even that much more tighter when comparing the two. The other thing is for geospatial is underground utility mapping. And there's commercial products already available. They're just really big right now. So there's gravimetric underground mapping. They take a gravimeter and they move it across somewhere. And because the gravity ranged from that, when you have the two gravimeters, one over the other, you get the profiling. They're able to detect a tunnel or a mine or a heavy deposit of some minerals, voids, higher density materials and layers under the ground with gravity. Also magnetometers, we're used to the magnetometers go out to detect underground pipes. Well, they're that much more sensitive. If they're quantum magnetometers, they can go deeper. Ground penetrating radar can only go so deep because we're limited in the power that we can put in them because the FCC, because you crank the power up higher, it's very dangerous for people. But the quantum magnetometer can read through materials better, clay soils, all kinds of matter. And we will see the commercial ones for use very soon that are that size, a handheld wand. Okay. A quantum, because it's sensitive, and the way it can reverse the role of photonic to electronic and electronic to photonic, it can improve cameras, digital cameras in lidar. It's actually happened already. Single photon lidar is a quantum-based technology that's actually commercialized. There's like a single photon lidar airborne scanner. We could be seeing that single photon on the smaller ground-based ones in the very near future, and in the imaging cameras. So one of the proposals that has been tested and proven already is using quantum entanglement, where you have a particle here that is mirroring the state of a particle somewhere else. And then you can do this differential when you're converting the photonic to electronic energy in a camera, and they get that much more sensitive. So a lot of the other tools beyond GPS that's used in geospatial, cameras, lidar, radar, mobile mapping systems will probably have quantum enhanced sensors on them within 10 years. There are challenges facing quantum sensing right now. So the quantum gyro navigation, the problem is they're huge vacuum pumps, big heavy chambers. You have adjacent to them, you've got these large cooling lasers. The whole systems are vulnerable to external noise and they're costly, but in a controlled environment like a submarine or a ship, they're going to work really, really well. We're likely not to see quantum gyroscopes in anything we would use in the field. It just, when they miniaturize, it could be by factors of a quarter, not 100th of the big ones that are out there. Gravimetry is the size of a trash can right now. The miniaturization, hopefully it's something that's portable enough in the field that, for instance, you could go out to a point on your project that you're going to map and you could get an absolute gravity reading and update that geoid model for where you're at right there on the spot. Quantum antennas, the size right now, they're about the size of a hot dog in a bun, but they could get miniaturized down to be in a GPS antenna casing, again, within 10 years. The power, though, and the cost, that's coming down rapidly. Magnetometry navigation that I showed earlier using the Earth's magnetic field, it's vulnerable to external noise sources. So if you tried to use it around a construction site or set of transmission lines or something, you might have problems. Okay, the technologies, all these technologies are proven. People have piloted them. There's even commercial quantum gravimeters being built and sold already. But miniaturization and integration is the next wave. So the next decade is going to be pretty exciting. Good news is, for example, like with the magnetometer, those have been built at chip scale. There are chip scale atomic clocks, not quite as precise as the ones in the satellites, but it's a step forward. Some other good news, about to launch any day now is what's called NTS-3. It's a testbed navigation satellite. It'll be in geosynchronous orbit. NTS-1 was launched before GPS was launched to test all the signals and technologies and codes and all that. So it's going to test all these new technologies, the anti-jamming, the anti-spoofing, the encryption, the better signals, and quantum plays a part in it. They've got multiple atomic clocks on these things. There's a really interesting encryption and key system that will eventually be usable by us in the field if we need it. And they have like directional phased arrays that they can aim the signals in conflict zones to bypass jamming and spoofing. So that's what's coming, or what's here and what's coming. Short answer is a lot of it doesn't apply to us directly, but by extension it will for surveying and mapping. And that's when I open it to questions.